You are watching session number 1 of the chapter Biomolecules. As a point of examination, maximum marks what we get is 6, question number 10 for 1 mark and question number 36 for 5 marks we are going to get. So biomolecules are nothing but the complex molecules present in a living system. Complex molecules present in a living system, we call it as biomolecules. The interesting thing is, the living things are made up of non-living particles like atoms and molecules. And these particles, if they are present in the living system, and these particles we call it as biomolecules. The molecules present in living system, we can say. Carbohydrate, if you consider, that is the best example for biomolecule. Proteins, lipids, nucleic acids, vitamins and hormones, all these are the examples for biomolecules. And in this session I am going to talk about the first part of this chapter, that is the carbohydrates. Later we will look over the protein, nucleic acids, hormones and some other examples. So let me talk about the first concept about this chapter, that is first biomolecule, that is carbohydrates. Carbohydrates. So first we will see what actually the carbohydrate stands for, and this word is quite familiar. We know that the food what we eat, example rice, contains carbohydrates, and that helps in supplying energy to our body. And carbohydrates are nothing but the sugar, what we guess, and the sweetening effect the substance is going to give. That is a common concept of what we know about the carbohydrates. But here literally we'll see what actually carbohydrate stands for according to chemistry. So let me write the statement for that one. Carbohydrates are nothing but they are optically active polyhydroxy aldehyde or ketone is nothing but carbohydrates. So we'll see what these terms stands for. Optically active. A substance is said to be optically active if it rotates the plane polarized light either in the left side or towards the right side, and this property we call it as optical activity. And the main condition for a compound to show optical activity is the compound should contain asymmetric carbon. Asymmetric carbon is nothing but the carbon which is joined with 4 different atoms or groups, that we call it as asymmetric carbon. Remember, most of the carbohydrates shows the property of optical activity, means that may consist of at least one asymmetric carbon and that rotates the plane polarized light. So that is the concept about the optical activity. Carbohydrates are optically active. And I have written hydroxy bond OH groups. So in the structure of carbohydrates we are going to observe bond OH groups, and we are not observing only one bond OH group, we are observing many OH groups here. Therefore polyhydroxy. Aldehyde or ketone, of course we have many hydroxyl groups, and apart from that you may get either aldehyde or ketone. You may get either bond CHO, that is aldehyde, or otherwise you are going to get a C double bond O where one is R and one is H. So you are going to observe either aldehyde or ketone. So that kind of organic compound that has to show optical activity, that has a more number of OH groups, and that may contain either aldehyde or ketone, and that we call it as carbohydrate. And one example I will give you. If you consider glucose as an example, see here, if you consider glucose as an example, glucose has asymmetric carbons, okay, and it has many OH groups, okay, and the functional group present in glucose is aldehyde. Whereas if you consider fructose, the functional group present is ketone. So either you are going to see aldehyde or ketone. Of course many polyhydroxy groups you are going to observe, and these compounds are optically active in nature, and these we call it as what actually the carbohydrates. And one example I will give you, later we will learn a number of examples for this one. So glucose is a very simple example for carbohydrate. The molecular formula of glucose we know. What is that? C6H12O6. So that is the name and the molecular formula of the simple carbohydrate, that is glucose. And carbohydrates can be represented in a form of one particular general formula, and the general formula is CxH2OY. This is the general formula for carbohydrate, where X and Y represents the number involved in carbon as well as water. So example, I am going to give you glucose. We know the formula is C6H12O6, and how we can write? I can write this glucose as C6 and H2O6. Is that right? Okay, so this is nothing but, see here, 6 carbons we have, hydrogen we have 12, and oxygen is 6. So C6H12O6, this glucose can be written in this form. Therefore, the carbohydrate can be represented in the form CxH2OY. But one more concept to remember, of course, n number of carbohydrates, okay, that satisfy the formula CxH2OY, and don't think that all compounds which satisfies the CxH2OY are not carbohydrates. One example I am going to give you here. So acetic acid we know, acetic acid, and the IUPAC name of acetic acid is ethanoic acid we know, and formula is known, that is CH3COOH. Okay, and here this CH3COOH I can write in the form of CH2H2O2. Is that right? See here, 2 carbons we have, okay, and 4 hydrogens we have, and 2 oxygen we have. Of course, this acetic acid follows the general formula CxH2O, but this is not carbohydrate. This does not belongs to carbohydrate. Why? Because in acetic acid we are not going to see any kind of aldehyde or ketonic group, and we are not going to observe polyhydroxy groups also. So therefore acetic acid actually that is a weak acid, isn't it? And therefore, even though that follows the general formula CxH2O, but that is not actually the carbohydrate. Okay, so this is one concept you should know about that. So finally, the carbohydrates are nothing but optical active polyhydroxy aldehydes or ketones. We call it as carbohydrates. Now, after knowing the concepts of carbohydrate, the meaning, and now we'll see what about the classification. What about the classification of carbohydrates? So we came to know what actually the meaning of carbohydrates, and now we'll see what about the classification of carbohydrates. So classification of carbohydrate, we have different criteria for that one. Okay, and based on the condition we are going to classify the carbohydrates. So actually the carbohydrates can be classified into 2 different criteria. The first one is how does it is going to interact with the water, and that we call it as hydrolysis. So the first condition is based on hydrolysis, how we are going to classify the carbohydrates. The second condition is whether the carbohydrate is reducing nature. So that we'll see nature later, that based on reducing nature of carbohydrates, and that is the one more condition how we are going to classify the carbohydrates. So first I am going to move with the classification of carbohydrates based on hydrolysis. Okay, so Roman number 1, and it is based on hydrolysis. So we'll see that one. Okay, so based on hydrolysis, how we are going to classify the carbohydrates here. And here the condition I told you that hydrolysis. So what is actually hydrolysis stands for? So remember, hydrolysis, water is going to be involved, of course. So the interaction with the water, okay, and that we call it as hydrolysis. So if you consider any substance and how it is going to react with the water, and that we call it as hydrolysis, and we have conditions for that one, and based on hydrolysis the carbohydrates are classified into 3 types. Okay, the first one is monosaccharide. The second one is oligosaccharide, and the third one is polysaccharide. So based on hydrolysis, carbohydrates are classified into 3 different types: monosaccharides, oligosaccharides and polysaccharides. So we'll move with the first one, that is monosaccharide. So number 1, I am going to talk about monosaccharide. Monosaccharide. So we'll see that one. Okay, monosaccharide. So what actually this monosaccharide stands for? So as the name indicates, mono, one. So if the carbohydrate has single simple unit, if a compound has a single unit of carbohydrate, and that we call it as a monosaccharide. And one more very important thing is, I told you that I am going to classify these classifications of carbohydrates based on hydrolysis. Let me give you one example. That is, if you consider one simple example, that is C6H12O6. Okay, interaction with water or a hydrolysis H2O. So glucose I am going to take and I am going to interact with the water, that we call it as hydrolysis. So try to remember, here you are not going to get any product here. So the question is, why you are not going to get any product? So one more example I am going to give you. If you consider sucrose as an example, sucrose, cane sugar, the formula is C12H22O11, and if that undergoes the hydrolysis, we are going to get the products. We are going to get again the single kind of monosaccharides of simple sugar we are going to get, and that is the completely different, that is sucrose. But whereas in case of monosaccharide, glucose is already a single unit of a carbohydrate and you cannot hydrolyze further. Okay, so that is the nature of a monosaccharide here. So remember, you cannot hydrolyze monosaccharides because monosaccharide itself is a single unit of carbohydrate. And the example I have written, so what is that example? Glucose is an example for monosaccharide. So now monosaccharide can be defined as a single unit of carbohydrate that cannot be hydrolyzed. That we call it as monosaccharide, and the example I have written here, that is glucose. Okay, so for your reference, the keyword I am going to write here, that is single unit of carbohydrate. Single unit of carbohydrate that cannot be hydrolyzed. That cannot be hydrolyzed. And that we call it as a monosaccharide. And example I told you already, glucose is the best example for monosaccharide. It has a single unit of carbohydrate and you cannot hydrolyze it further. Okay, so that is about the first type of carbohydrate, that is a monosaccharide. So now it is all about the type based on hydrolysis, that is a monosaccharide. So now I am going to talk about the second one. Second one is oligosaccharide. Second one is oligosaccharide. So we'll see what actually oligosaccharide stands for. So we know the previous one, that is, if any carbohydrate that won't undergo hydrolysis, and that is referred as a monosaccharide. Okay, but if you consider any carbohydrate and after hydrolysis, okay, after hydrolysis, on hydrolysis, if you get 2 to 10 monosaccharides, if you get 2 to 10 monosaccharides, and that we call it as a oligosaccharide. Okay, so try to know that one. We have the carbohydrate, and if it undergoes hydrolysis, and sometimes you are going to get 2 monosaccharides or 2 simple form of carbohydrates, sometimes 3, 4, similarly up to 10 monosaccharides you are going to get. So on hydrolysis, if you get 2 to 10 monosaccharides, and that carbohydrate we call it as oligosaccharide. So oligosaccharides can be defined as carbohydrates which produces 2 to 10 monosaccharides after hydrolysis. On hydrolysis, that we call it as what actually? The oligosaccharide. Okay, and if you compare the examples, and the most familiar and most common type of oligosaccharide is disaccharide. So if the carbohydrate produces only 2 monosaccharide, that we call it as disaccharide. If it produces 3 monosaccharide, that we call it as trisaccharide. Similarly, tetrasaccharide, like this it continues. Okay, the most common is disaccharide. I am going to discuss here. Disaccharide. So disaccharide is one type of oligosaccharide. Remember, disaccharide is nothing but if any carbohydrate, okay, and on hydrolysis, if it gives only 2 monosaccharide, if it gives 2 monosaccharides, and that we call it as disaccharides here. So we'll see this particular disaccharide with an example. Okay, one familiar example I am going to consider, that is C12H22O11. C12H22O11. This is the molecular formula of sucrose or cane sugar. I told you hydrolysis we have to carry out, that is nothing but the reaction with the water, and actually this is acid hydrolysis. In the presence of any dilute acid you are supposed to carry out this reaction, and I hope you can guess what would be the products. And the products are C6H12O6, and one more you are going to get, that is also C6H12O6. So two single form of carbohydrates we got. So actually this is sucrose, okay, and when sucrose undergoes hydrolysis, and this one is particular, this is glucose, and one more you are going to get, that is fructose. Of course the molecular formula are same, but the structure is going to be different. I told you already what is the main difference between glucose and sucrose. Let me repeat that one. In a glucose the functional group is aldehyde, whereas in fructose the functional group is a ketone, and both contains polyhydroxyl groups here, and both are optical active in nature. Therefore these two belongs to a class, we call it as carbohydrates. Okay, so what happened here? So this is the original carbohydrate, and after hydrolysis, okay, and what you got? You got two monosaccharide here. Glucose is monosaccharide, fructose is also monosaccharide, and you just further hydrolyze this, you are not going to get any product. Similarly, if you further hydrolyze fructose, you are not going to get any product, and based on that condition I can say glucose and fructose are nothing but monosaccharides here. So therefore on hydrolysis of sucrose we got two monosaccharides. Therefore what I am going to say, sucrose belongs to disaccharide, or I can say sucrose is one example that belongs to oligosaccharide also. So on hydrolysis if you get two monosaccharides, that we call it as disaccharide. Similarly one more example I am going to consider, that is the raffinose. Okay, remember if you hydrolyze raffinose we are going to get three monosaccharides, and that we call it as a trisaccharide. Similarly the term continues, we can write the n number of examples for that one, and that is about the example for disaccharide. So let me explain some more concept of what I explained already in some other chapters also. And if you just observe this example, and this example we call it as inversion of cane sugar, isn't it? In the chapter called surface chemistry I explained the same example, that is inversion of cane sugar. And do you remember which enzyme is involved in the reaction called inversion of cane sugar? The answer is invertase. We used to write here. Okay, so invertase is enzyme, and this you can call it as enzyme catalysis also. That is the one concept, the same equation we use. And in the one more chapter called chemical kinetics, and this is the well-known example we can write for pseudo first order reaction. You just recall what I explained about pseudo first order reaction. Higher order reaction can be converted into first order reaction by considering all other reactants in excess except one. We call it as pseudo first order reaction. The rate of this reaction depends only on the sucrose, but water we take in excess quantity, that will be considered as a constant here. Therefore the second order reaction is converted into first order reaction in this case. Therefore this is the best example for pseudo first order reaction. So this is some other concepts, what I explained already some other chapters also. And now you remember the sucrose is an example for disaccharide, because on hydrolysis the sucrose gives two monosaccharides, the one is glucose and one more is fructose. Okay, so that is about the second type, that is oligosaccharide. Similarly we can write a trisaccharide and a tetrasaccharide like that. The third one I told you already, the third one is polysaccharides. Third one, polysaccharides. So we'll see what actually the polysaccharide stands for, as the name indicates. Now I hope you can guess what would be the meaning of polysaccharide. Monosaccharide on hydrolysis you are not going to get any product. In oligosaccharides on hydrolysis you will get the monosaccharides from 2 to 10 range. If you get only two monosaccharides on hydrolysis we call it as a disaccharide. Polysaccharides, if you consider any carbohydrate and if you carry out a hydrolysis, we are going to get a large number of monosaccharides, and that we call it as what actually the polysaccharides here. So polysaccharides are nothing but on hydrolysis on hydrolysis, you are going to get what actually the large number of monosaccharides you are going to get. Large number of monosaccharides. Okay, and one simple example I am going to consider, and that is C6H10O5, that is N. C6H10O5, and remember this is the molecular formula of starch. You just try to know that one. This is nothing but the starch. I will link with one more concept. I discussed the chapter called polymers. And do you remember in which classification of polymer this starch belongs? Starch is the best example for natural polymers. They are found in plants. Okay, and this starch is formed by n number of repeating units, and we are going to get this polymer, that is starch. The formula is C6H10O5 bracket n, therefore large number we have of this one. So if you consider this starch as an example, and if you carry out a hydrolysis, that is H2O. Okay, so since n number of the repeating units we have NH2O, I am going to consider, and in the presence of acid hydrolysis here, and we are going to get the monosaccharide, that is glucose, C6H12O6, large number n we are supposed to write here. So here we got to 2 actually, therefore disaccharide we said. Here n number of this single unit we are going to get, and that we call it as the polysaccharide here. And starch is an example for polysaccharide, cellulose is an example for polysaccharide, glycogen is also an example for polysaccharide, and that is all about the different classification of carbohydrates based on hydrolysis. That is the first condition. So based on hydrolysis we have monosaccharide, oligosaccharide and polysaccharide here. And remember this one, this is the quite important one. Glucose never undergoes hydrolysis. And if any substance undergoes hydrolysis, if you get 2 monosaccharide, that is disaccharide, and a large number of single units of carbohydrates if you get, and that we call it as polysaccharide. And one more point to just try to know, carbohydrate if you consider, if you take glucose and if you consider sucrose, the sugar what we use in kitchen, that is actually the sucrose. Remember, the sugar is nothing but sucrose. Okay, and that has the sweetening effect. Okay, so usually the monosaccharides and these oligosaccharides, they are called sugars. Why? Because that provides the sweetening effect. Whereas if you taste starch, and you are not going to feel any sweetening effect, therefore polysaccharides are called non-sugars. You try to know that one. This is important one, non-sugars. So monosaccharide and oligosaccharide, they are sugars, whereas polysaccharides are non-sugars. Why? Because if you consider example of a starch, that won't give the sweetening effect. Okay, so that's why the polysaccharides we call it as non-sugar, and that is about the first condition, that is the first criteria, the classification of carbohydrates based on hydrolysis. And now we'll see the second type of classification of carbohydrates. The second type is reducing and non-reducing sugar. Reducing and non-reducing sugar. The first one will see what actually reducing sugar stands for. Reducing sugar. So now this reducing and non-reducing nature of carbohydrates we'll see now, and here this is the practical concept. You are going to perform the experiment in the lab. We are supposed to consider 2 reagents. One is Fehling's solution and second one is Tollens reagent. So the first one is Fehling's solution, and one more is Tollens reagent. Okay, so if any carbohydrate, if that reduces these 2 reagents, that may be Fehling's solution or Tollens reagent, and that carbohydrate or sugar we call it as a reducing sugar. So what actually this Fehling's solution and Tollens reagent stands for? Fehling's solution is nothing but alkaline solution of copper 2 sulfate. If you consider the alkaline solution, soluble bases are called alkalis, we know that one. So alkaline solution of copper sulfate, copper, the valency will be 2 here. So copper 2 sulfate, the color is blue in color, we know that one. So that solution we call it as failing solution. And tolerance reagent is nothing but that is ammoniacal silver nitrate. Ammoniacal silver nitrate, that is the AgNO3. If you take a little amount of AgNO3 and if you dissolve in a right proportion with NaOH and NH4OH, sodium hydroxide and ammonium hydroxide, you are going to get a mixture of solution that we call it as ammoniacal silver nitrate solution. We call it as a tolerance reagent. So a carbohydrate or a sugar that reduces the failing solution and tolerance reagent, that we call it as reducing sugars. So the question is why this reduces actually the failing solution and a tolerance reagent. The reason behind that is that has free aldehyde or ketonic group. If the free aldehyde or ketonic group is present, and that has to reduce these two solutions, that is a failing reagent and tolerance solution. Otherwise, if it is not free aldehydic or ketonic group, and that won't reduce these two reagents, and that we call it as what actually the non-reducing sugars. In short, I can say the sugar which reduces failing solution and tolerance reagent, we call it as reducing sugars. Examples. Remember, all monosaccharides are reducing sugars only. Very simple example, glucose. Remember, usually all monosaccharides belongs to reducing sugar. So, if you consider glucose as an example, and if you perform a test called failing solution test or tolerance reagent test, that has to reduce. There is a color change or physical appearance is going to be changed in the experimental data what you are going to collect. And glucose is an example for reducing sugar. And one more I am going to consider maltose, and one more I am going to consider lactose. Okay, so later we are going to learn about these two, and right now you remember maltose and lactose are reducing sugars. They belong to a category called disaccharides. What's the meaning of that one? If you consider maltose or lactose, and if you carry out hydrolysis, we are going to get 2 monosaccharides here. Of course, these two are disaccharides, that is going to reduce the failing solution and the tolerance reagent, and that's why these we call it as reducing sugar. So try to know reducing sugar that reduces failing solution and tolerance reagent. The opposite of that, the second one, that is non-reducing sugar. Non-reducing sugars. And now I hope you can guess that does not reduces. The first one is failing solution. And one more is, what is that? Tolerance reagent. And that is why we call it as a non-reducing sugar. And the well-known example for that is sucrose. You just try to know that one, sucrose. And we know that sucrose belongs to a category we call it as disaccharide, because on hydrolysis we get 2 monosaccharides. They are glucose and fructose. And remember, in the structure of glucose we are not going to see free aldehyde or ketonic group. Since there is absence of a free aldehyde or a ketonic group here, and this sucrose belongs to a category that we call it as a non-reducing sugar, and that does not reduce a failing solution and a tolerance reagent. The observation will be as same as it is. Okay, and that is all about the second classification of sugar. One is reducing sugar and one more is non-reducing sugar, and that is the second type, the second condition, based on whether it reduces failing solution or not, whether it reduces tolerance reagents or not. Okay, so try to know failing solution is nothing but alkaline solution of copper sulfate, that is blue in color, and a tolerance reagent is nothing but ammoniacal silver nitrate, we call it as a tolerance reagent. And give importance to the examples here which reduces these solutions or which does not reduces the tolerance, and one more is the failing solution. And that is all about the second type, that is classification of carbohydrates. So that is all about the concept called classification of carbohydrates. Previous one was discussion solution based on hydrolysis, and this is based on whether it reduces the failing solution and tolling solution or not. So this is all about the classification. So now after the classification, we'll see the first type based on hydrolysis, what I discussed, that is a monosaccharide. So now I am going to talk about monosaccharides. Monosaccharides. Okay, and now I hope you can guess, monosaccharides are nothing but they are carbohydrates, and that does not undergoes hydrolysis, and that is a single unit of a carbohydrate only. Okay, and that reduces the failing solution and a tolerance reagent, we know that one. So this is the basic concept what we already know, and now we'll see some other concepts related to that. So let me consider example, and I am going to explain that. And if you consider CH2OH, one example I am going to consider. So this is one carbohydrate, later I am going to explain about that, and one more I am going to consider, that is CH2OH, C double bond O, and CH2OH. Let me write the names of this. This is glyceraldehyde, and the second compound is dihydroxyacetone. So these two are the examples of monosaccharide. So what I am going to discuss here is, so now I am going to talk about two terms, and the first term is, what is that? Aldose. Okay, and the second one I am going to talk about is ketose. So try to know, monosaccharides we classify into two main types. One is aldose and ketose. So what is the meaning of that one? Okay, and if you observe this example, glyceraldehyde, later we are going to learn about all these things. So right to remember, this is the structure of a glyceraldehyde, and if you observe carefully, okay, and see here we have OH groups. Okay, and in this compound also we have OH groups, polyhydroxy, and here we are going to observe asymmetric carbon. Actually this is the asymmetric carbon because this is going to be linked with four different carbons. Okay, four different groups or atoms. Okay, and one more very important thing is, in a glyceraldehyde the functional group is CHO. What is that? Aldehyde functional group. And if you consider dihydroxyacetone, you know, acetone formula I hope you remember, CH3, C double bond O, CH3, that is the first member of ketone. Propanone is the IUPAC name, and H is replaced by OH and H is replaced by OH, dihydroxyacetone. Okay, and in this case the functional group is this one. What is that? C double bond O. Okay, so in the monosaccharide, if the functional group is aldehyde, that we call it as aldose. Remember, in aldose we are going to observe aldehyde as a functional group. Whereas in case of dihydroxyacetone, that is an example for ketose, and you are going to observe what is that? Ketone. Of course you can consider, you know, any two alkyl groups here. So a monosaccharide which consists of aldehyde, that we call it as aldose. The monosaccharide which contains ketone as a functional group, that we call it as ketose, and that's why the name we have, what is that? Aldose and ketose. So this is a very important thing you should know. I told you already, in one carbohydrate we are not going to observe both aldehyde and ketone. Either you get aldehyde ketone as the meaning of carbohydrate says. So in this case we have aldehyde, therefore aldose. In this case we have a ketone, therefore that is the ketose here. Okay, so that is the one concept about aldose and ketose here. Similarly we can classify in general also. So I am going to explain that how you are going to consider. So number of carbon atoms we will see. Number of carbon atoms, and what is the general name we are going to see here. If the carbon atom is 3 and the name we call it as triose. See here, in the monosaccharide, number of carbon atoms we have 3, that we call it as triose. So if you consider glyceraldehyde as an example, how many carbon we have? 1, 2, 3 carbons we have. Therefore this we call it as a triose. This tri indicates the carbohydrate with 3 carbons here. If the number of carbon atom is 4, we call it as tetrose. If it is 5, we call it as pentose. If it is 6, we call it as hexose. If it is 7, we call it as heptose. This is the general name for indicating the monosaccharides. Okay, so try to know that one: triose, tetrose, pentose, hexose, heptose. These prefixes or the starting term indicates number of carbon atoms present in the monosaccharide here. And I told you that one, in monosaccharide you may get aldehyde or one more is a ketone. So let us assume this is the aldose I am going to consider and this is the ketose I am going to consider. Means in this case we have aldehyde as a functional group, and in this case we have ketone as a functional group. And how we are going to name that? Okay, one example here, this is the glyceraldehyde. If you consider as an example, 3 carbon we have, therefore triose. And what is the functional group present here? Aldehyde. So therefore you can name it as aldotriose. See here, aldotriose. So what is this aldo stands for? Aldo stands for the functional group is aldehyde. What is this triose stands for? 3 carbons we have. Let us assume, if you consider this dihydroxyacetone as an example, and how many carbons we have? 3 we have. That is nothing but triose. But what is the functional group? Functional group is ketone. Therefore, how you are going to get here? This you can call it as ketotriose. This we call it as ketotriose. Similarly, if aldehyde is present in tetrose, you can call it as, what is that? Aldotetrose. Okay. Similarly here, aldopentose. Similarly, aldohexose. And the last one is aldoheptose. Similarly, I am going to write if the functional group is a ketone, and here we call it as, what is that? Ketotetrose. And for this one, ketopentose. And for this one, ketohexose. And the last one is ketoheptose. So that is the name you can indicate if the functional group is aldehyde or if the functional group is ketone, and these indicates the number of carbon atom present in that. Okay, so this is actually the classification of monosaccharides, what we can consider. Okay, so this is the simple example what I considered. And remember, monosaccharide contains aldehyde, we call it as aldose. Monosaccharide contain ketone, we call it as the ketose here, and these are the names. So based on that, we just add the prefix called aldo, and one more is the keto, and you are going to get the name of the monosaccharides. Now we'll discuss about the well-known example for monosaccharide, that is glucose. So the concepts what we know already are, glucose is an example for monosaccharide, right? And that won't undergo hydrolysis, and that is a single unit of the carbohydrate, what we can say. So what is the main source of glucose? We'll see. What is the main source? Of course, glucose is present in n number of plant source you can consider, and it is the amount of glucose is high in case of ripe grapes. And one more example is honey. The quantity, the amount of glucose will be more in these two cases. And remember, glucose I can call it as aldohexose. So try to know this one, aldohexose. I explained the different classification of monosaccharides. Glucose is nothing but aldohexose. So now I hope you can guess what would be the meaning of this aldohexose. Aldohexose, aldose means the glucose contains aldehyde functional group. Hexose, how many carbons we have? 6 carbons we have. Since glucose has 6 carbon atoms and aldehyde functional group, therefore glucose you can call it as aldohexose. And the chemical name of glucose is dextrose. So try to know that one. Dextrose is the chemical name of glucose. We'll talk about structure and all these things later. That is the fundamental concept you should know about the glucose. So now we'll see what about the preparation. The preparation of glucose we'll see. How we can prepare glucose. and we know that glucose is a monosaccharide here, and well-known reactions we know that one is from sucrose. How we can prepare sucrose is nothing but cane sugar. Okay, you can consider cane sugar, that is nothing but the sucrose. From sucrose, how we can prepare glucose? We know that reaction very well, I explained that already. Sucrose C12H22O11, when it undergoes hydrolysis in the presence of dilute acid, we get C6H12O6, one is glucose and one more is, what is that? Fructose. That's it. That is how we can prepare glucose from cane sugar. And how we can write the statement? Glucose is obtained by hydrolysis of cane sugar. That is how we can write the statement for that one, and that is the first method of preparation of glucose, that is from sucrose. The second one is from starch. How we can prepare that? This reaction also we have seen. I am going to repeat that. From starch, how we can prepare glucose? And we know that starch is nothing but non-sugar, because that is a best example for polysaccharides, and on hydrolysis it gives large number of monosaccharides. C6H10O5, since it is polysaccharide, braces with N I will write, and it undergoes hydrolysis, and we are going to get what actually the large number of glucose units we are going to get. So starch on hydrolysis, we are going to get the glucose here. So these two are very simple methods of preparation of glucose, one from sucrose and one from starch. And now we'll see about how actually the glucose structure is. Okay, so now we'll see elucidating the structure of glucose. Elucidating structure of glucose. Elucidating is nothing but we will see how actually the glucose structure is and what are the components present in that. Briefly, so glucose molecule and what are the functional group, how many OH we have, and some other related concepts we are going to explain along with the reaction, and that complete explanation or elaborating the structure of glucose, that we call it as elucidating the structure of glucose. Okay, so now the first thing what I am going to say here is, when you consider the glucose and the molecular formula we know, that is C6H12O6. Okay, and how we can write that? CHO, CHOH 4 times and CH2OH. This is one simplified form, condensed structure you can say. Condensed structure of glucose I have written here. And remember, we have CH, that is nothing but aldehyde. Okay, and we have polyhydroxy, 4 OH we have, and one more OH we have, polyhydroxyaldehyde it is. Okay, and that is a simple structure of glucose what we can consider, and try to know the molecular formula is C6H12O6, and we can write in very simple method, and that I consider it as the first point, that is the elucidating the structure of glucose. Now second one we will see how does the glucose reacts with the hydrogen iodide and what is the conclusion drawn from it. I am going to explain here. Okay, so with Hi, hydrogen iodide. So now let me write the reaction and later we'll see what is the conclusion drawn from it. So glucose structure I am going to draw CHO, CHOH 4 times. CHOH, the same group is going to repeat. Okay, and in the below we have CH2OH, and that is the structure of glucose. Okay, so remember, when you take glucose and when you heat glucose with red phosphorus and Hi. Red phosphorus is one of the allotropic forms of phosphorus. Hi, that acts as reducing agent. So the combination of red phosphorus and Hi will be the reducing agent what we are going to use here, and we have to heat that. And if you take the glucose and if you perform this condition, if you heat the glucose in presence of red phosphorus and Hi, we are going to get one product, and let me write that CH3, CH2, 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 and one more is CH3. 1, 2, 3, 4, 5, 6. So how many carbons we have? 6 carbons we have. Carbon carbon single bond, and I am going to name this as what actually hexane. Since all carbon atoms are present in a chain form, single chain form, and I call it as normal hexane or N-hexane. So this is a reaction what I am going to consider, and what I am going to say here is when glucose is heated in the presence of red phosphorus and Hi, N-hexane is obtained. Try to know that one. Since this is a reducing agent that reduces the aldehyde, primary alcohol, secondary alcohol, and finally we are going to get a simple alkane that is a normal hexane. N stands for normal since the carbon chain or the carbon atoms are in a straight chain manner. That is a reaction when glucose reacts with red phosphorus and Hi. The main reason behind this reaction is we need to understand what is the purpose of this reaction. From this reaction, what is the conclusion we can draw it here? So since you just see, if you here we are going to get a N-hexane as a product, and one can say that the original structure of glucose that contains 6 carbon atoms in a straight chain. That is the conclusion. Okay, just try to know, by this reaction, by this experimental data, we came to know that the glucose contains 6 carbon atoms in a straight chain, and that is how using this reaction we can explain one of the property of glucose. Okay, so try to know how the reaction is and how the question would be asked from this. In the examination, you may get that, show that or prove that the glucose contains 6 carbon atoms in a straight chain, and what we have to do. So how we came to know that the glucose contains 6 carbon atoms in a straight chain? By this reaction. When you take glucose and when you heat that in presence of red phosphorus and Hi, we got N-hexane. From this experimental data, from this reaction, we came to know that the glucose contains 6 carbon atoms in a straight chain, and that is the conclusion drawn from it. Okay, so the first point is the molecular formula of glucose is C6H12O6, and the second point is glucose has 6 carbon atoms in a straight chain, and that I came to know from this reaction. Some other properties we'll see, the third one, and in that I will classify A and B. The A one will see what happens with NH2OH. Do you know what is that NH2OH stands for? Hydroxyl amine. For your reference I will write here. NH2OH stands for hydroxyl amine. So now we'll see when we take glucose and when we react with the hydroxyl amine, what is the product we are going to get and what is the conclusion drawn from it we are going to see. So what would be the structure of glucose? CHO, CHOH 4 times and CH2OH. So that is the structure of glucose what we know, and when this reacts with hydroxyl amine, that is NH2OH. So what is the product we are going to get, we'll see now. So now for this one, let me explain in a very simple manner what is the function of hydroxyl amine we are going to see. So just see here, I am going to write here, if you consider any carbonyl group, carbonyl acid, any carbonyl, that may be aldehyde, ketone, acid chloride, ester, whatever it may be, any carbonyl, and when you react with the hydroxyl amine, what is the formula? NH2OH. Here NH2OH, just in reverse manner I have written NH2OH, that is hydroxyl amine, and during the reaction of carbonyl and hydroxyl amine, there is elimination of water takes place. H2O is going to be eliminated. So after elimination of water, what we are going to get? C double bond NOH we get here, and this kind of a compound we call it as oxime. Know this one. So oxime is nothing but if we have a C double bond N, and usually that is referred as oxime here, NOH we are going to get here. How we are going to get that? When any carbonyl reacts with the hydroxyl amine, there is elimination of water, we are going to get oxime. Okay, and now I will link, that is the basic reaction what you should know, and I will link the same concept in this case. So we have a glucose and we are going to react with the hydroxylamine. Just keep in mind, hydroxylamine is going to react with the carbonyl. So which is the carbonyl here? Aldehyde is the carbonyl, the example what we have here. So this carbonyl and reacts with the hydroxylamine. There is elimination of water, and there I represented it in a very simple manner. Here H2 and O is going to be eliminated. So what we are going to get here? Here we are going to get CH double bond NOH here. If you remove the water, okay, oxygen is removed, CH we get here, and H2 is removed, NOH we get here, C double bond NOH. The remaining thing I will write as it is, that is CHOH 4 times, and below I am going to consider what is that, CH2OH. And what is this? This is oxide. Okay, and this is nothing but glucose, and you can call it as the glucose oxime. The name of this compound is glucose oxime, or you can say oxime of glucose. You can say both are same, glucose oxime or oxime of glucose. So that is the reaction you should know. Okay, and this is in particular example with the glucose, but in general you can remember like that. That will help you in CET. And this is how what actually the hydroxylamine reacts. If hydroxylamine reacts with carbonyl, definitely you are going to get what is that, oxime. So now the very important thing is, what is the conclusion drawn from it? In the previous case we got N-hexane, and what we said, the glucose has a 6 carbon atom in a straight chain. Now in this case, carefully you observe, hydroxylamine that is going to bind or react with the, here we have aldehyde. In general what I said, carbonyl. So from this reaction I can say glucose contains carbonyl group. Okay, when glucose reacts with the hydroxylamine, we get oxime of glucose. The conclusion drawn from it is the glucose contains carbonyl group. We'll see one more example of the same kind. The A1 I discussed about hydroxylamine. The B I am going to talk about with the hydrogen cyanide, HCN. With hydrogen cyanide, when glucose reacts, what is the product and what is the conclusion drawn from it? So we'll see that one. Okay, so now we'll see the glucose structure. CHO, CHOH 4 times, and CH2OH. This is a glucose, we know that. And when it reacts with HCN, hydrogen cyanide, what is the product we are going to get? We know when glucose reacts with HI and red phosphorus, we get N-hexane. When glucose reacts with the hydroxylamine, we get oxime of glucose. Now we'll see when glucose reacts with HCN, what we get. So let me explain that as simple, how I am going to explain here. We know that one HCN that will ionize in presence of a base, you get H plus and Cn minus. Let us assume this is the carbonyl what I have. When you consider Cn minus, electron rich species, that is the nucleophile, and this nucleophile is going to attack on this carbon deficient, and the pi electron is going to shift here, and what we are going to get? We will get a CO minus here, okay, and these two bonds are there, and here we have Cn. So this is just as the addition of Cn to carbonyl. And now what happens here? This undergoes hydrolysis in presence of H plus, and finally we are going to get what actually OH we get, and here I am going to get a Cn. That is the mechanism involved in case of addition of HCN to carbonyl group here. So try to know this one. Initially I had the carbonyl. After addition we got 2 groups as OH and one more is Cn. So this is the mechanism, and now I will come to this original reaction what I have when this glucose reacts with the hydrogen cyanide, and we know that one the carbonyl here is the aldehyde one. So what we are going to get here, let me write that main part first. So CH will be the same thing, one you get OH and one more you get a Cn here. So here I will write OH and here I will write Cn here. The remaining group will be as it is same, that is CHOH 4 times we get here, and below I am going to write CH2OH here, and after addition of HCN the compound what we get, and that we call it as cyanohydrine. So this is cyanohydrin, and particularly you can say glucose cyanohydrin. So what happened in this reaction? When glucose reacts with the hydrogen cyanide, we are going to get the product as glucose cyanohydrin. So what is the conclusion drawn from it? You will get a cyanohydrin when you have a carbonyl, when it is going to react with HCN only. So from this reaction also we came to know that the glucose contains carbonyl group. So these two are the same. That is nothing but the reaction with the hydroxylamine and the reaction with the hydrogen cyanide. When the glucose reacts with the hydroxylamine, you will get oxam. When glucose reacts with the hydrogen cyanide, you will get a cyanohydrin. From these two, I can say the glucose contains the carbonyl group. That is the one more elucidating the structure of glucose. So now we will see the fourth one. Okay, in fourth one we will see what happens when the glucose reacts with the bromine water. We will see that one, when glucose reacts with the bromine water. So we will see that one, what happens in this case. So now CHO, CHOH 4 times, that is the structure of glucose, what I am going to consider. And when this undergoes the reaction with the bromine water, Br2 water, and I hope you know bromine water is the best example for oxidant, you can say, that helps for oxidation. Okay, so this is oxidizing agent. Bromine water is oxidizing agent. So that has to oxidize the original, the compound or the glucose what we have. So we'll see in general the concept about that. So if you have alcohol, I hope you know this one. If you have alcohol, when you carry out oxidation, okay, and we are going to get aldehyde. If you have aldehyde, when you carry out oxidation, we are going to get carboxylic acid. This is the fundamental concept of oxidation, that we know that. Okay, if alcohol on oxidation, you get aldehyde. Aldehyde on oxidation, you will get a carboxylic acid. One more concept, if you have a primary alcohol, you will get aldehyde. If you have a secondary alcohol, you will get ketone instead of aldehyde. So try to know that one. In case of secondary alcohol you are going to get a ketone, and on oxidation you are going to get a carboxylic acid here. And if you take the reverse of that one, that we call it as the reduction, and reduction means we are supposed to consider H plus, isn't it? That is the reduction. Reduction of carboxylic acid you will get aldehyde, and reduction of aldehyde we are going to get what actually the alcohol, and that is the fundamental concept of oxidation and reduction that we know. Okay, so now we'll come to this one. Since bromine water is oxidizing agent, that has to oxidize the given compound what we have, and the given compound is the glucose. And what is the functional group? The functional group is aldehyde, and we know that one aldehyde on oxidation we are going to get carboxylic acid. Since Br2 is oxidizing agent, aldehyde is going to be converted into carboxylic acid, that is COH, and the remaining thing as it is CHOH 4 times we have, and below we are going to get what is the CH2OH. So glucose on oxidation with the bromine water we will get this compound, and this we call it as gluconic acid. So try to know the name, gluconic acid. So gluconic acid is obtained by oxidation of glucose in presence of bromine water. Here the reaction is important, but the conclusion is more important from that. So what would be the conclusion drawn from it? I hope we can guess. Aldehyde is going to be converted to carboxylic acid in presence of bromine water. Oxidizing agent we added here, and we got carboxylic acid here, and the original substance must contain what actually the aldehyde functional group. So what is the conclusion drawn from it? The glucose contains aldehyde functional group. That is the conclusion drawn from it, and that is about the one more elucidating structure of glucose, that is the reaction with the bromine water. And now we'll see the one more reaction how we can write, that is with acetic anhydride. With acetic anhydride. So what happens when glucose reacts with the acetic anhydride? We'll see, and later we'll see one more reaction, what happens when the glucose reacts with the strong oxidizing agents like a concentrated HNO3. Okay, so now we'll see what happens when the glucose reacts with the acetic anhydride. Okay, and let me explain using the reaction, and CHO CHOH 4 times and CH2OH, that is glucose. And when this reacts with the acetic anhydride, you can write acetic anhydride, the name itself, but I am going to write the formula for that one. That is CH3O twice O. CH3O twice O, that is the formula for acetic anhydride. Recent days we are using abbreviated form of that one, that is AC2O. If we are consider AC2O, that is as good as acetic anhydride only. Remember, AC stands for CH3O. Okay, we have twice of CH3O and we have O, acetic anhydride. Okay, and now you remember, in any reaction, if you add acetic anhydride, the process going to take place is acetylation. For your reference, I will write here. The process going to take place is acetylation. Okay, and now the question arises, what actually acetylation stands for? So what is the meaning of acetylation? If you know what is acetylation, then it would be easy to write the product of this one. So let me explain what is the acetylation stands for. So now observe here. Let us assume I have alcoholic group, bond OH, polyhydroxy, can say H. If H of OH is replaced by CH3O, if H of OH is replaced by CH3O, CH3CO, and that we call it as what actually acetylation. Okay, so now in case of glucose, now you observe how many OH we have. In case of glucose, if you consider how many OH we have totally 5 different OH here. Now see, here we have 4 OH and here we have one more OH. We are going to react with the acetylation. Okay, sorry, make one correction. CH3CO, sorry for that. CH3CO and CH3CO. If H of OH is replaced by CH3CO, and that we call it as acetylation. So now we are going to see here. Here we have OH and here we have OH. We'll see what happens here. Now CH2 remains as it is, CHO. Okay, so now here we have a CHO. Remember, H of OH is replaced by CH3CO, that we call it as acetylation. So H I am going to replace it by CH3CO. Bracket 4 we have already. Okay, H of OH is replaced by CH3CO. And one more, here we have CH2O. Here also we have OH, and H of OH I am going to replace it by CH3CO. And here also I am going to write, what is that? CH3CO, and that is the product what we are going to get. Okay, and the process involved is acetylation. And what is the reagent used for acetylation? Acetic anhydride. What is the formula? CH3CO twice O. You can see AC2O you can write here, and the meaning you try to know, if you have a OH, H is going to be replaced by CH3CO, that we call it as acetylation, and we are going to get this product. Okay, and now the question is, what would be the name of this one? Okay, the name of this one is, just if you observe, originally we have 4 OH groups, 5 OH groups, and last we got how many acetyl groups we just substituted? Totally we substituted 5. Therefore the name of the compound will be glucose pentaacetate, you can consider. So let me write here, and this is glucose pentaacetate. Since we have 5 acetate groups here, so glucose pentaacetate we are going to get, and that is the reaction, and that process we call it as acetylation. Now the question arises, what is the conclusion drawn from it? So now see, here HCl we added and we got a cyanohydrin. The conclusion was the glucose contains carbonyl. In this case, oxidizing agent we added, we take oxidation, and the conclusion drawn from it is glucose contains aldehyde. Now see, what is the main thing happened here? In this case, there is no change in the aldehyde. Okay, we don't bother about that. So H of OH is replaced. H of OH is replaced. So what is the conclusion drawn from it is the glucose contains 5 hydroxyl groups. You try to know that one. Glucose contains 5 hydroxyl group. Why? Because out of 5 hydroxyl group, the hydrogens are going to be replaced by, what is that, a CH3CO, that we call it as acetylation. The conclusion drawn from it is, the glucose contains 5 OH groups. So now in particular, see here, this OH is going to be attached with the carbon, and particularly we call it as alcohol. And now we know that alcohols can be classified into primary alcohol, secondary alcohol and tertiary alcohol we know. And what kind of alcohol this is? This is a primary alcohol. Try to know, this is a primary alcohol. Why? Because the carbon of the alcohol is going to be linked with only one carbon. This is a primary alcohol. So how many primary alcohols are there in glucose? One primary alcohol. And if you consider this OH, okay, and this OH is carbon linked with this carbon, and this carbon is linked with 2, therefore this actually that is a secondary alcohol. So 5 OH groups we have, and out of 5 OH groups, 1 that is a primary alcohol and remaining 4 that is a secondary alcohol. That is the conclusion drawn from the reaction that we call it as acetylation, and the reagent will be acetic anhydride, CH3CO twice O. Okay, and from this reaction we came to know the glucose contains 5 OH groups. The last one we'll see what happens when glucose reacts with strong oxidizing agent, that is HNO3. Remember, HNO3, nitric acid, is strong oxidizing agent. What happens in this case? So let me explain that. CHOH 4 times and CH2OH. So when this reacts with HNO3, and HNO3 is a strong oxidizing agent we know, okay, and now I hope you can guess, since HNO3 is a strong oxidizing agent that undergoes oxidation, and all the functional groups what we have, that is going to be converted into what actually the carboxylic acid. So CHOH 4 times I am going to write, and this is COOH I am going to write here, and the name of this compound will be saccharide acid. This is saccharide acid. Okay, and one more concept I am going to write here. Okay, and when you consider gluconic acid, the gluconic acid we know, this is the structure of gluconic acid, COOH, CHOH 4 times, and this is a CH2OH. This is a gluconic acid. This is a gluconic acid. Remember, when gluconic acid undergoes oxidation with a strong oxidizing agent like HNO3, we are going to get the same product, that is a saccharide acid here. Okay, and what is the conclusion drawn from it here? We'll see now. Okay, in the previous case, we came to know that 5 OH groups will be present. I explained here which one is primary and secondary, but the existence of primary alcohol will be confirmed by this reaction. When a strong oxidizing agent HNO3 is added to glucose, we are going to get a saccharide acid. When strong oxidizing agent HNO3 is added to gluconic acid, we are going to get a saccharide acid only. So what is the conclusion drawn here? Aldehyde is converted to carboxylic acid, it is okay, but this is the primary alcohol. Primary alcohol is also converted into carboxylic acid. Okay, one conclusion we came to know. But in case of gluconic acid, carboxylic acid remains as it is, whereas this primary alcohol is converted into carboxylic acid. From these two reactions, this is a one reaction and this is a one more reaction. From these two reactions we came to know that the glucose contains one primary alcohol. This is the primary alcohol, and I explained already, and these OH groups are nothing but the secondary alcohol. This is the one more conclusion what we drawn from the reaction of a concentrated HNO3, and all these are the 6 reactions I explained. From all these reactions we came to know the glucose structure, what it contains. In simple, I can say the molecular formula is C6H12O6. When glucose is heated in the presence of red phosphorus and Hi, we get N-hexane, and the conclusion is the glucose contains 6 carbon atoms in a straight chain. When glucose reacts with hydroxyl amine, we get oxime of glucose. When glucose reacts with hydrogen cyanide, we get a cyanohydrin. From these two reactions, the conclusion drawn is the glucose contains carbonyl group. When glucose undergoes oxidation in presence of bromine water, we get gluconic acid. What is the conclusion drawn from it? The glucose contains aldehyde group. When glucose reacts with acetic anhydride, we will get to glucose pentaacetate. The process involved is acetylation, and the conclusion drawn from it is the glucose contains 5 OH groups. The last one is when glucose and gluconic acid both undergoes oxidation in presence of strong nitric acid and we get the saccharic acid, the conclusion drawn from it is the glucose contains one primary alcohol. So from these reactions we came to know what glucose contains. And that is all about the elucidating structure of glucose. So now just we elucidated the structure of glucose. So now we have not seen what is the exact structure of glucose. So what is the exact structure of glucose, what it contains, and what about the different methods of writing the structure of glucose, that we'll see in the next session. Thanks for watching.